Hello guys. What I love the most is to see great documents for school because you can see very quality questions imposed by teachers. Today I prepare 8 questions from school that covers the integration by parts and possibly something called the reduction formula. So let's get to it. I believe you can feel the direct love from the teacher when they organize the materials in their PPT, in their homework, and assignment, and I want you to feel that love from a school when they were learning the integration. Okay, integration by parts, as you know, is one of the most advanced technique of integration in AAHL. It uses the antiderivative of the product rule, right? And it's focusing on choosing which function you need to differentiate to reduce the form so that you can work with the integral as just one function. Okay, this is one of the typical example which covers the product of the exponential and trigonometric. And as you know, this is one of the interesting examples because considering which function to differentiate doesn't really matter, right? Because we cannot reduce it because this transcendental function exponential or the cosine after the nth derivative still preserves the form of its kind, so we cannot reduce it. But you know that you need to do by parts twice on this particular example so that we can come up with the example of the like term that you started with and you rearrange. Let me show you the algebra of solving this problem in the next slide. All right, let's have a look at the question. So now we got the product of the exponential and the cosine. It does not matter which one you have to choose to differentiate to reduce the form. So what I decided to do is to differentiate the cosine and then integrate exponential. So if you do that, so now we have the initial form of the cosine. You integrate the exponential, but now we got the composition of a 2x, so you know the 1 over 2 comes out. So we just did that, right? And then you integrate next one with the product of the derivative of the cosine and integral of the exponential. It's fine. So something that we already know of. And then as you can see, you have to also apply the integration by parts on the sine 2x times 2x, right? So we're gonna do that, and then what we need to do here is getting the like term, right, of the sine 2x. Cosine 2x, and then we're gonna rearrange to the other form. Hence, we can put them in the multiple of 2, and then divide both sides by the 2. And as you can see, for the constant, even if you divide by the 2, it's going to be the same thing. So it's actually okay. Therefore, what we see here is the product of the exponential and cosine being the 1 over 4 times e to the power of x, and then the rest of the product. And you're gonna get the same result even if you do, even if you start with the integral of the, for example, cosine 2x, and you should check yourself if you get the same thing. But this is a very typical integration by parts technique. If I have a product of the exponential and cosine, it's often asked because we don't know which one to reduce, so it doesn't matter. However, you have to do by parts twice so that you're gonna have the like term again with some multiple so that you can combine them later after the rearrangement. So that was the example of this exercise, and let's move on how things can get more spicy with the other. All right, let's have a look at the question number 4 from that practice where it talks about some sequence, right? That this IN integral is now to integrate x to the power of n times the exponential, and as you can see, it's asking you to describe the recursive form. So the recursive form shows that my sequence depends on the previous term, as you have already seen from the arithmetic sequence or geometric sequence, right? For example, the geometric sequence. My present term depends on the constant multiple of the previous term, right? That's the first order recursive relation. And a similar thing is Fibonacci sequence, which of course can be a popular choice of a paper 3 problem. But let's have a look at how a recursive form can be applied in this example. All right. Let's have a look at the initial case where we had to integrate to the I naught, just exponentially. That's okay. Now let's have a look at deriving the recursive formula. So we start with this. As you can see, we're going to do the integration by parts. The one that I'm going to start differentiating is the polynomial. So we start with the integration by parts while differentiating the polynomial, hoping to reduce, and we got this recursive form. Very lovely. And you can apply this for the I1, I2, I3. Let's see that. So for the I1, it's going to depend on the I naught, which you already have found. So you can just substitute in. And for I2, as you can see, I can work with the I1 and etc. So this recursive relation is quite popular for the integration by parts, which also was seen before in the exam. Let's have a look at an exam question that uses the recursive form and show you that this is actually quite popular form of practice, which can also be extended for potential paper 3 practice. This is why I think I was thrilled to see this practice from school, because it really shows that teacher wants to challenge the students and then hopefully prepare them well accordingly for the paper. Yeah, this is actually a very popular exam question from past paper, and this was actually to derive a recursive form so that you can use it for the volume formula. So I'm not going to delve into the question too much, but then I like to look at the second part from the C, where it shows to derive the reduction formula. So let's have a look at that. All right, so what we have to do here is to show this recursive form by the integration by parts. So namely, what you have to do is to decide you're going to differentiate the logarithmic form. The ln x to the power of n are the one that I'm going to differentiate, and then 1 over x squared is the one that I'm going to integrate for the parts. But it's because if you keep differentiating 1 over x squared instead of the logarithmic form, you don't really reduce it, you see. You keep creating more power for the function, so differentiating on the 1 over x to the power of 2 doesn't really help. But instead, if you differentiate the logarithmic form, it actually helps to reduce the form. So integration by parts is really to know which function I have to differentiate to reduce, right? So here I perform the definite integration by parts. I really strongly encourage you to do by yourself as well, but the step is clear, and hence we derive this formula. And in the question, what you have to do is you have to do the I think 4, something like that, when you have to square the function twice, and then use the formula accordingly, and which is pretty straightforward. So it's a very nice practice question from the exam. So please help yourself to attempt. Sure. And then the next example, the question number 6 from that package from the school, it goes over this very beautiful integration practice with the x to the power of n and sine x. And you're going to see many times this integration by parts with the product of the polynomial and sine is very important and very popular. And then later on, you get to see the power of a sine or cosine with the integration by parts. And it's actually just paper 1 or paper 2 practice. And let me just quickly show you how the integration is going to go. All right, so if I look at this, the integral of an and bn, you can just do it by parts, no problem. And as you can see, I chose the the polynomial to reduce. So the x to the power of n is preserved, and x to the power of n will be differentiated as the integration continues. And as you can see, because of the integral of the sine becoming the negative cosine, we actually substitute with the bn minus 1, as you can see, so which I've just done. And the same thing for the bn. If you integrate that by parts, keeping the x to the power of n as the differentiating form, and then we get this following form. It's just a typical integral by parts, right? So then, however, what we can do is to substitute things out, right? Because the an minus 1 can be substituted with the recursive relation that we already have defined before. So as you can see, the an will be can be described as the another recursive form that in this time just expressed as an minus 1 instead of mixing with the an and bn. So always describing the sequence in terms of its previous one helps rather than introducing new terms. So help yourself that you can do the integration by parts these two, and then see if you can also substitute to come up with that. So it's actually fine. So it's pretty straightforward. But instead of working with the x to the power of n, I like to show you what happens if you actually integrate the power. The power of the sine or cosine is actually very typical recursive form of integration by parts technique question. So let's continue to have a look at that. So let's extend this problem a bit. All right, let's have a look at this integration by parts paper 3 style problem. Paper 3 style problem that involves something called the reduction formula. Reduction formula is just a fancy name of doing the integration by parts many times. And what I want to show you, check this out. You want to prove this statement for the n being positive integer, right? And every time you have a statement, proof of a statement with the positive integer, it's very likely to associate with the proof by induction. So what I'm going to do is to start with the induction and show you how this can be utilized for the other style. So now we're going to have a look at the even power of n. Okay, and you often see actually the even power of a sine in the exam. You know, the power of 2 and power of 4 and 6 often use either half angle for the power of 2, and for the power of 4, 6 is often used with the complex number in DMT. But let's see the generalized form with the induction by part. Let's see for the induction. Let's get to it. All right, as you know, every time we have a inductive statement, every time we have a statement with the positive integer, is very likely to work with the proof by induction. So I like to work with the induction, starting with the basic step. So if I put n equal to 1 for my statement, I got the sine squared to integrate, and as you know, it's something to do with the half angle formula. So I use the half angle formula to integrate, and I strongly advise you to use the definite integration by definite integration for this one. Hopefully you get to derive the pi over 2. That's not a problem. So our next step is to show you the induction hypothesis implies the result to prove. So for the induction hypothesis, I'm going to start with the n equal to k true. So that's my inductive hypothesis, and our aim, my friend, the result to prove is the following. I have n is equal to k plus 1 true. So that's my the result. So for that one, what we are going to use the formula that we have derived. Okay, let's have a look at this one. So before we attempt with these sine indefinite integral from 0 to pi over 2 of a sine to the power of 2k plus 2, let me quickly show you how we can use this general form of the reduction formula of the sine. The sine to the power of n, if you do the by parts twice, you get to realize that it can be reduced up the sine to the power of n minus 2, you see. So if we then apply this one for the definite integral, what you see here is that the first term will actually vanish, because if I put 0 for the sine, whatever the power, such as n minus 1, will become 0. If I put pi over 2, cosine will become 0, so that's simply 0. So it's only the second term with the n minus 1 over n being the coefficient would remain. Okay, and then you remember something of 0 to pi over 2 of a sine integral becomes 1. So finding the pattern of the odd power, such as a 3 or 5, will be used. And please remember, sine to the power of 2k was already given in our induction hypothesis, and finding the pattern from the previous slide with the odd power, which is now we're extending to the 2k plus 1, will be given as such. And please remember the formula, the general formula of the reduction formula of a sine to the power of n from 0 to pi of 2 was given as such. And now we want to use it for our general case. So the result to prove was the sine x to the power of 2k plus 2, right? That's the result that we had to do. But if you use the general formula, right, of the reduction formula, we can actually reduce down to the power of 2k with this coefficient, right? And then that to the power of 2k is in fact our induction hypothesis, which we can replace. And then as you can see, the rest we can sub it in, and then extending the term by one more term with the 2k plus 1 in the numerator and 2k plus 2 in the denominator, and that actually comes the second part of the inductive proof. Therefore the statement is true for the positive integer by the principle of mathematical induction. So now we actually have generalized the even power. And let's see if there's something more we can actually derive from this proof to extend with the paper 3 problem. Sure, so let's try to use the integral that we were using, the one with the reduction formula, and we were supposed to show that the integral of the I to n is that inequality. I mean, we already have the result of the I over 2n, right? That was the previous one, right? The even power, so we can use it extensively, but we just have to find the size of it, right? But I want you to realize the sin x is actually strictly increasing from 0 to pi over 2, and it's the range is bounded by 0 to 1. So if you actually power any number in between 0 and 1, it gets smaller. So as you can see, the highest power, which is 2n plus 2, is going to be the minimum because it's an increasing function between 0 and 1, right? So we can have the integral here, and then taking the definite integral property, the direction of inequality for such positive values will remain the same. So we can actually conclude from 0 to pi of 2 of the integral at the following, which is indeed the I to n plus 2 in the lower bound, I to n plus 1 in the middle, and then the I to n for the upper bound. Yeah, I think it's a mistype. Should have been the 2n. I will amend that. All right. So as we have defined the in as the integration from 0 to pi of 2 of the sine sine and x, and as you can see, those integral will become the replacement of the sequence term, the in. So it's going to be I2n plus 2, I2n plus 1, and I2n as desired, right, from the part A. Sure, the next question was to ask about the ratio of the I2n plus 2 over I2n to be the following ratio. And then it's pretty straightforward. I mean, if you use the definition that we already have, then cancel out all the odd terms and even terms. Talking about the last remaining, that's going to be simply 2n plus 1 over 2n. 2, right? So that's exactly what we have so far, and that's the ratio we have. Sure, let's have a look at then, try to use this all the information they gathered together to talk about this essential inequality that we are going to eventually use for the squeeze theorem. And then let's have a look at what we have so far. So we have the first part was to derive the inequality, and then the second part was the ratio of the I2n plus 2 and I2n having this ratio. And then what we can do here is to introduce that value with the, and then let's suppose that we're trying to divide everything by I2n. If you do so, you have this inequality, and then since we already have the ratio for the I2n plus 2 over 2n, you can replace them. And then the I2n over I2n, the upper bound is actually the same thing, so hence becoming 1. So the ratio between the I2n plus 1 and I2n is in fact given as the following inequality. And then what lovely thing can happen is actually applying the squeeze theorem and then realizing that the lower bound and upper bound, both of them will converge to 1. And hence by the squeeze theorem, whatever in between the I2n plus 1 over I2n will actually converge to 1. So that's great. Okay, let's have a look at the last part of the question where it was talking about the bunch of product of even consecutive in a row and then the odd consecutive in a row would actually result in pi over 2, which is known as the Wallis product, and we can actually derive it from the definite integration by reduction formula that we have derived from the sine to the power of 2n. So let me quickly show you that. So let us please gather what we have so far. First of all, from the last part, we show that the ratio between the I2n plus 1 and I2n actually converges to 1. That is great. And using, the definition that we have derived from the which was the I2n, of the general formula, we have this ratio. That is lovely. That's great. And then we also know the ratio of that from the first part will converge to 1. That's great. So as you can see, what we can do is we can simply just rearrange the pi over 2 to the other side, right? And then do the the ratio product between the fraction on the top and fraction on the bottom. So you get the product of the numerator each and the denominator each, right? So that we have this following beautiful result. Yes, as you can see, using the algebra to simplify further, we can see this product was called the Wallis product as becoming d over 2. And I think this was a great opportunity for me to introduce you a very nice problem discussed often in a school. And from there, you can feel the care and attachment of the teacher who is willing to challenge the students with the very formulated way, right? By preparing a nice document, nice level of questions to handle out the upcoming exams, right? And whenever I get a chance to hold of those problems, I like to share with you by analyzing those problems why the question was asked. The point of all this with the paper 3 with the reduction formula is that how we can actually extend what we have learned from the integration by parts, right? So extending it to show you that we can many times to reduce the form because the integral now becomes in terms of a sequence. And whenever you deal with the sequence, it is often to associate with the limit of the sequence or the sum of the sequences. And for today, we saw this Wallis product using the sequence as the limit. But obviously, other type of a paper with integration by reduction formula is present. It can also be sometimes with the series, and that's also another interesting problem that I can impose maybe next time. So that was pretty much it for me today. Hope you have a great day, and I'll see you next time. Thank you.